Bismillah Rahman Rahim. Dear students, today we are going to study experiment 5 of automatic control system in testing 3. Okay. Experiment 5 is about the controller types. We are going to start with the first experiment, which is about the PID controller, and we are going to study about its characteristics here. The second one is about the PD controller, and the third part will be about the performance criteria of the automatic control loop here. So, to start with the first part, which is about the PID controller, what we said that, for example, in the PID controller, the D component of the PID controller is going to generate a theoretically infinitely high pulse at the time point t0. As shown in the figure, at t0, we are going to get an infinitely high pulse here for the real derivative action in the ideal PID controller here. But what happened here, the pulse is limited by the technically finite manipulated variable. Like for example, for the output, we are going to have an op-amp there, and this op-amp can have only maximum output voltage here. So what happened inside, instead of the high infinite pulse, we are going to get basically the finite pulse value here. Okay. Now what he said that normally whenever we want to apply the real D component, it is going to give us a very excessive amplitudes here. So what we do here, in order to avoid this one, normally the D component is implemented as a time delay element of the order one here. Now for the experiment, the setup is simple. What we have done, we have the analog controller here, and we have configured this analog controller as the PID. You can see here in the switches, we have used like the P and I and D as on here just to configure it as the PID controller here. Once we configure this experiment as a PID, we are going to run the step response plotter here, and the result shows that the result you can see here. Okay, this blue line is basically your input signal here, which you give to the controller, and this green line is basically the output of the controller here. It's quite clear here that initially we get a high pulse here, but since this high pulse is not infinite, it is around 14 here, 14 volt here. The reason here is the presence of the operational amplifier here. Okay, the second thing here is, since the D component is not used as a time lag here, like we have directly applied the D component here, so it means the step response which we are getting is very distorted in nature here. Okay, the second experiment, or the second part of the experiment 5, is about the PD controller. Means we have only proportional and the derivative components of the controller here, and we don't have the integral here. Now what he said that normally the I component of the PID controller, we can remove it. When we can remove it, we will remove it whenever the elimination of the remaining error signal is not necessary here. Like we don't need to remove the remaining error signals here, or sometime in the controller itself it is equipped with the integral action component here. So in such cases we can remove the I component to make it as the D component here. Now for the PD component, basically we are going to discuss about the rate time calculation for the ramp response of the PD controller here. Okay, this is the experiment here. So what we have basically, to get the ramp response, the input should also be a ramp signal here. Now what we have, if we give the input ramp at certain point t naught here, what we are going to get, we are going to get the response which is for the PD control, which is the ramp response here. Now for this ramp response, we want to calculate the value of TV here. Now what is the TV here? TV is basically if I expand back this ramp function backward toward the x-axis here. So the point at t naught and this point, this is basically your TV here. Okay. So to find this value TV, which is basically the rate time here, and it is the time spent by which the certain value of the manipulated variable, which is the y here, is reached at a faster rate than what will be reached with the proportional action control here. Okay, so if we want to find the TV here, it is normally not possible in the system we have basically. So what we will have, just to find this point, what we will do, whenever we have a ramp response here, we will try to use a tangent line here, which, and we are going to draw it in parallel with the response here. Okay, so then we are going to find this one. This point is going to be the TV value here. So to find the T value, again, the experimental setup is here. Again, remember here, the important point is we have configured the controller as PD here. The I component here is off, so it means this will work as a PD controller here. Now, the results, if you see here, the result is we have two lines here or two signals here. Y1 at channel 1, Y1 is basically your input signal, which is a ramp signal here. Y2 is the response of that ramp signal here. Now, to check the value of TV, I already told you we need to expand. We need to take this one back to the x-axis here, which is not possible in the available system we have or the available software which we have. What we will do here, instead we will draw a tangent line here. So from here in the controls here, you need to select the tangent here. What you will do when you get a tangent here, if you remember something from the previous experiment, how we draw the tangent here, whenever you take the tangent is going to be something like this. So basically what we have here we have two things. We have the scale which are horizontal here, and we have two scales which are basically vertical here. So we are going to, first of all, what you will do, first of all, you will take the lower scale here, horizontal scale, and you need to place it around this point here. You will take the upper scale here and you need to adjust it here at this particular point here. Okay, next thing is you need to adjust this point at the initial value where you started with your input here, and this point will be the point which is basically touching the ramp signal here, touching basically this point here, you can see. Okay, so basically once you do like this, what will happen, this value from here to here is going to tell you the value of the TV, which is basically 1.05 in our case. Okay, if you see the explanation here, the TV is the time span between forwarding the ramp function at the controller input and the point in which the manipulated variable has reached double the value of T naught. Means if I expand it back, so this will be basically the double value here. This value and this value as we shown earlier here. Okay, so the TV is going to be approximately 1 second here. The third part is about finding the performance criteria for the automatic control part. Here we are going to do, or we are going to calculate the three things. We are going to calculate the overshoot, we are going to calculate the error signal, and the third one we are going to talk about the rise time and the settling time here. Okay, so first of all, for example, what is overshoot? If my signal, this is my signal, which is the response of the system, this is the steady state value, like it's settled down here. Now, if I have some value which is higher than the steady state value, which is x naught here, we will say that we have an overshoot here. Okay, so normally what we have, the highest value here and this lower value, this is known as the overshoot, and we are going to represent them in the form of a percentage here. Okay, you can see here, like the overshoot is defined as the maximum set point deviation of the control variable here. Okay, and the control variable here is x here. Second part here is basically the rise time and the settling time here. Okay, rise time he has called is as Tn or T on here, settling time as T off here. Now, if you want to find, or if you want to calculate the rise time and settling time here, before that we need to discuss about the tolerance band here. Tolerance band is nothing but for this steady state value, which is here, the 10% upward and the 10% downward here. Okay, so this is your tolerance band here. So you can see the tolerance band is 10% upward around the final steady state value of the control variable. So basically this yellow area is the tolerance band here. Now to find the rise time and the settling time, the rise time will be from the start of the output or the response here up till the point when the first time it enters the tolerance band here. So this value or this time is going to be your rise time here. The second one is the settling time. The settling time will be like, for example, you have a steady state response with the pulses here. Okay, so what happened? The last time when it enters the tolerance band, we need to mark this point, because after that it will not come out of the tolerance band, it will remain inside the tolerance band. So this point and the start point, we call this one as the settling time or T off here. Okay, so this is what we are going to calculate in our experiment today. So this is the experiment setup here. Simply the important thing here is we are using the proportional action coefficients. We are going to use the proportional controller here. Okay. Now first thing here which we wanted to find the EB here. EB means the error signal. So simple is what you have. This one, this blue line is your input, which is basically the step response here. The second one is this line or this waveform is basically the response of the system here. Now this is the point where it has got settled here. Okay, so this point and the point where you have your input signal, the remaining or the input and the distance between them will be your error signal here. Okay, ideally what we want this response to be at the input here, to settle down around here. So you can see here the red horizontal red curve value is 1.01, and the set, what you can say here, the static value or a steady state value of the response here is 0.92 here. So when you subtract both of them, so you will get 0.09, which is the error signal here. The second one is about the overshoot here. For the overshoot, what we have, first of all, we have highlighted this steady state value here. So the steady state value is shown with the horizontal green curve here, which is 0.9. So this is your steady state value here. Now what is the overshoot amplitude here? The overshoot amplitude is 1.27 here. Okay, so the difference between the two is basically 0.35, which is here. So to calculate the overshoot, what you will have, you will take this value, the difference between the two here, and you will divide it with the steady state value. Okay, so when you divide it, you will get 38 point something, and we need to represent them using some percentage here. The next result is about calculating the rise time and the settling time here. So first of all, what we have, we are going to talk about this steady state response here. For this steady state response, first of all, we need to, like for example, this value. For this particular value, we are going to calculate the 10% up and the 10% down here. So this green line and this line is basically nothing but this is your tolerance band here. 10% up and down of the steady state value. Okay, why we need this tolerance band? Because we need to decide about the rise time and the settling time here. Now, first of all, what we have from the start here means shown in the vertical red cursor here up till the first time when the response or the output X signal enters this point. You can see this point, the distance between the yellow and the red here is 0.55. This is your rise time here. Okay, we will call it as the Tn here. The second one is the settling time here. So I told you that in the settling time, it is going to be the time when last time it will enter the tolerance band. So last time it enters at this position. So this position and the starting position. So this position and the starting position is going to be your settling time, which is basically here shown as like this one. This value, which is this value basically, which is shown as 1.76. And this is obviously your rise time, which is 0.55. If you add both of them, you will get 2.3, which is basically your settling time here. Okay, so this is all about today's experiment. Thank you so much. Assalamu alaikum.